This lesson deals with supplemental problem 211. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 23. The circuit shown here is called an overvoltage indicator. It consists of two LEDs, plus and minus 10 volt power supply, 1K resistor, and an input. Could you find the values of the input which would cause the green or the yellow LED to light, assuming that it takes about a milliamp of current for the LED to begin to light? Once you examine the results, if they're not symmetric, could you redesign it so that it is symmetric? I'll explain that when we get to part B. Supplemental problem 210, we had a green LED that had a turn-on voltage of about 3.5 volts. So let's replace this LED with an ideal diode, here to here, and a 3.5 volt battery, and then a 10 volt battery back to ground. The yellow LED in supplemental problem 210 had a forward voltage around 2.2 volts. Let's replace this by a 2.2 volt battery in series with an ideal diode. And then from this node back to ground, I've got minus 10 volts. You might notice that this is the same schematic we had in Chapter 2 on page 39 for the double clipper. A lot of circuits, when you redraw them, become things that we've looked at before. I'm hoping that by the time you finish this course that you don't need to redraw something to figure out what it's doing. If you recall from the double clipper, current flows this way. In this case, the green LED would be on. And when current flows this way, the yellow LED would come on. So let's assume that we have a current coming out of V in of at least 1 milliamp. If current's flowing this way, we're going to treat the ideal diode as a short circuit. I have 3.5 volts in series with 10 volts, so that's 13.5. Current can't go this way, so we'll make this an open circuit. Now we'll analyze the circuit. The rise in voltage is V in. The drop is I sub D1 times 1K plus 13.5 volts. If the current starts to increase more than 1 milliamp, then this term is going to get bigger, or our input's going to be greater than the drop across here plus 13.5. 1 milliamp times 1K is 1 volt, so that's 14.5 volts. Is this diode off? Well, if this is on, then the voltage here is a minus 12.2, and this node voltage is 13.5. A negative number minus a positive number is negative, so that diode is off. And once the input is greater than 14.5 volts, current will begin to flow, at least 1 milliamp, and the green LED will turn on. Let's take a look at current going in the other direction. Current flows in this direction, and the yellow LED lights, and our ideal diode is a short. We have a 2.2 volt forward drop added to a 10 volt drop from the power supply, and that gives us 12.2. And that would really mean that, of course, that V in is actually negative, that current's going to be flowing in this direction. Now, to write our equations, we have to follow the original notation for V in. The rise in voltage is V in, and then the drops are on the loop. Because current's flowing in this direction, I'm going to have a negative drop of 1K times I sub D2, and then minus 12.2 volts. If the current begins to increase, then this term's going to get larger and we'll get more negative. V in is going to get smaller, same equation, minus 1K times current of at least 1 milliamp, and then 12.2 volts. Whenever V in is less than or equal to 13.2, the yellow LED lights. We should check that diode D1 is off. Let's find the voltage across. It's going to be this node voltage, which is minus 12.2 minus 13.5, which is a negative number. Diode D1 is definitely off. This is kind of an alarm system. It tells you whether a voltage is a certain size, positive or negative. The results are not symmetric. In other words, we turn on the green LED when we have a voltage greater than or equal to 14.5 volts. And then we have the yellow LED light whenever we're less than or equal to minus 13.2. Make it so that it's the same in both directions. So I need to change this from minus 13.2 to minus 14.5. Let's go back to this case again. I need to basically increase the drop across this battery, and I can do that by putting a resistor in series with it, have current flowing in this direction. And I want to get the total voltage here to be the same as it was for the green LED. It was 2.2 for the yellow and 3.5 for the green. To get 1.3 volts dropped across this resistor, I'm going to have at least 1 milliamp flowing through it. And to get 1.3 volts, when I have 1 milliamp through that, that's 1.3K. So here's my final design. When the voltage is positive and greater than 14.5 volts, current flows in this direction, and we get the green LED to light. And when this goes negative, it goes in this direction, and it's roughly minus 14.5, and we get the yellow LED to light. And this is supplemental problem 211.